Hi everyone, and welcome to part 2 of the Spatial Variability lecture series. My name is Brigid Cami. I'm a geotechnical software developer at Rocscience. My colleague Sina, Javankhoshdel, and I will be presenting this lecture. So this is the second lecture in our spatial series, and in this video we'll be introducing spatial variability into our probabilistic analysis. We'll start with a brief overview of the first lecture, then we'll introduce the concepts of spatial variability, and then go through some examples in slide 2. So let's start with a quick overview of the last lecture. What's the difference between deterministic analysis and probabilistic analysis? A deterministic analysis takes the parameter input as a single value. So cohesion is 2 kilopascals, for example, and so it runs a single analysis, computes a single factor of safety. A probabilistic analysis, on the other hand, takes parameter inputs as distributions. So say cohesion now is a normal distribution with a mean of 2 ranging from about 0.5 to 3.5. Then that distribution is sampled, and samples are assigned to a set of 1,000 simulations, for example. So this first simulation would take cohesion of about 0.7 and compute the factor of safety. The second would take cohesion of 2 and compute factor of safety, and so on. Then the probability of failure is calculated as the number of simulations with a factor of safety less than 1 divided by the total number of simulations. Okay, but why should we bother with a probabilistic analysis? The short answer is that we can't say we're 100% confident in our single cohesion value, and so 100% confident in our single factor of safety value. In this plot on the right, we have the factor of safety distributions for two slopes, slope A and slope B. Slope A has a mean factor of safety of 1.7, whereas slope B has a mean factor of safety of 1.5. So if we were to look at just deterministic factor of safety, we would say slope A is safer than slope B. However, the coefficient of variation, which is defined as the standard deviation or the spread of the data divided by the mean, is larger for slope A. You can see here it's more spread out. And we can see that it's a coefficient of variation of 0.3 for slope A compared to slope B, which is 0.15. And so the probability of failure, which is defined as the area under the curve to the left of the factor of safety 1 line, this gray region, is larger for slope A than slope B. And so that means that even though slope A might have a higher FS, it actually has a higher chance of failing when compared to slope B. So now we'll go over the steps involved in setting up a probabilistic analysis in slide 2. The first step is defining distributions for our parameters. That's done in the material statistics dialog in slide 2. Here we can define the distribution type, such as normal, and the associated parameters such as mean and standard deviation and the bounds. If we don't have enough data to calculate the standard deviation, we can use this coefficient of variation table from this button to estimate the value. So with that, we can use one of the COV values from literature found in the table and multiply it by our mean to get a standard deviation if we don't have enough data. Okay, so that's step 1. Now that we've defined the distributions for our random variables, we need to sample them. So we define the sampling method and number of samples in the project settings dialog. Latin hypercube is the recommended sampling method. More information on this can be found in the first lecture. And we might define 1,000 samples. That means our distributions are sampled 1,000 times. Now those 1,000 samples are assigned to 1,000 separate simulations. So the first simulation might have a cohesion value of 0.7, and the factor of safety is calculated for it. And so on, the 1,000th simulation might have a value of 3.3 and the corresponding FS is calculated. So we have our 1,000 simulations, 1,000 factor of safeties. Then the probability of failure is defined as the number of simulations with FS less than 1 divided by the total number of simulations, 1,000 in this example we're looking at. So that gives us a brief overview of probabilistic slope stability analysis. The other thing we covered in the last lecture is the concept of cross-correlation. Based on what we've covered, Latin hypercube might sample a low value of cohesion and a low value of friction angle and plug them into a simulation. But we know that low cohesion values tend to be paired with high friction angles, so this simulation is not very likely. We don't want to consider it equally with a simulation such as this one. So we want low cohesion values to be paired with high friction angle values. Well, we can do that by defining a cross-correlation coefficient between the two. And that's done in the material statistics dialog as well. We add an intermediate step here and define our coefficient by using this correlation button. We can also define coefficients between other parameters in this dialog and between materials, which can be quite useful. Okay, and finally we wrapped up the first lecture with the geotextile reinforced wall example. We talked about how considering cross-correlation in our analysis makes our PF more accurate and hence lower. So here we have the top row without cross-correlation has a probability of failure of 10.8%, while the bottom row with cross-correlation has a probability of failure of about 6.8%. However, the deterministic factor of safety in this example is bigger than 1.3, which means it's certainly in the range of design, while a probability of failure of almost 7% certainly isn't. So are we still being over-conservative? Can we be more realistic? Okay, well, what we're doing now, by defining distributions, sampling them, and assigning the values to simulations, is known as the single random variable approach, or SRV. It makes one very big assumption which we haven't yet considered, and that is that it assumes that in each simulation the slope is homogeneous, so that the cohesion at x equals 0 is exactly the same as it is 100 meters away, for example. We don't want to make such a strong assumption, so instead of using our distributions this way, we can use it this way, so that the sampled values are assigned to cells within each simulation. And our simulations are no longer homogeneous, but instead consider different arrangements of samples, such that each simulation is spatially variable in a different way. So let's talk about how we can consider spatial variability in our analysis in slide 2. The procedure for running a spatially variable analysis is almost identical to that of a regular probabilistic or SRV analysis, with the addition of one new step. And that's this define correlation length step, which, after spatial variability is enabled, is defined in the same material statistics dialog. So let's talk about what this correlation length value means. Okay, we said we can consider spatial variability by just taking our same distribution and assigning it to cells within each simulation instead of to the entire slope in each simulation. There's only one problem here. If this distribution is sampled randomly, according to Latin hypercube, then we might get a very low cohesion value in this cell, such as 0.7, and a very high cohesion in this cell, such as 3.3. But it's unlikely that cohesion would abruptly jump like that in nature. We would expect it to be a gradual shift. So we need some way to constrain cells that are near each other so that they are similar. And that's where the concept of correlation length comes in. Correlation length is the distance over which the values of a random variable are correlated or similar. And the best way to understand that is through visualization. Okay, so let's say we've defined a distribution for cohesion. It has a mean of 2, a standard deviation of 0.5, and it ranges between about 0.5 and 3.5. Let's start with the deterministic case. If we pick two locations on this slope and look at the cohesion value, they'll be the same, 2 kilopascals. That was our mean. Now let's look at SRV, or simple probabilistic analysis. Say this is simulation 1 out of 1000, for example, which means a value from the distribution has been assigned to this slope in this simulation. Then if we pick two locations on this slope, the cohesion is the same, and it's whatever was sampled, 1.2 kilopascals, for example. The correlation length here is infinity. That means that the distance over which values are correlated or similar is infinite. It's the entire slope, because the value of cohesion is exactly the same throughout the slope. Now let's look at a slope with spatially varying cohesion. Notice the legend on the left here. We see that in this simulation, cohesion ranges from about 0.5 to 3.5 kilopascals. If we pick a location here, we see it's blue, and so C is about 0.5 kilopascals. If we pick a location near it, it's green, so cohesion is about 2 kilopascals, again, just from looking at the legend. These two locations are more than 1 meter apart, which means they are more apart than the correlation length of 1 meter defined in this simulation. That means that the values assigned to these two locations have a negligible correlation. Also notice that correlation length of 1 meter means that the cohesion field fluctuates a lot. Okay, now if we have a larger correlation length of 20 meters, say, we see that the field is much smoother and there's less fluctuation. Now if we pick a location here, we get a cohesion of 3 kilopascals, and here we get a cohesion of 1 kilopascal. Once again, because these locations are more than 20 meters apart, the correlation between them is negligible. Another way of looking at it is that areas that are going to be similar in values are going to be about 20 meters by 20 meters, such as here, where we see a generally blue region, or here. Okay, so now we have a general idea of what correlation length is. How do we get this value? The geotechnical field is notorious for always having limited data. However, in most cases, we have some sort of CPT or SPT data. And if we have that, we can measure correlation length. There are well-established methods for measuring correlation length from CPT data, and more advanced methods have been coming out recently that use the likes of Bayes when data is insufficient. And if resources are limited and we don't have any CPT or SPT data, we can use literature to estimate correlation length. In the material statistics dialog, we have a table that summarizes correlation length data from literature by material type by clicking from this button. Okay, so we've defined our distributions, we've defined our correlation length. The next step is generating our fields, as such. So each of our 1,000 simulations would have a different arrangement of weak and strong areas. And then a factor of safety is calculated for each of these simulations or fields. So now, how are these fields generated exactly? Well, this is certainly not something you need to know as a user, but we've provided a little background here on the field generation. In slide 2, we're using the local average subdivision method, or LAS, to generate these fields. There are many field generation methods available, but this is the most suitable for our purposes due to its speed and accuracy. This generation method accounts for many things, but basically what it does is it draws a boundary box around our slope. It subdivides that into 4 cells, and one of the requirements these cells must meet is that the cohesion values assigned must average to the mean of the cohesion distribution. Then each of those cells is subdivided and the new cells must average to the parent cell, and so on, until we arrive at our desired mesh size. As such, if you're wondering how do you know what the desired mesh size is, slide 2 takes care of this for you. We have an algorithm that calculates the mesh size based on the boundaries of the model and the correlation length. Okay, so now we have our fields. We want to calculate factor of safety for each field. Say this is simulation or field 1 out of 1,000. There are 2 ways to view these fields in slide 2. We can either view the mesh we just discussed, or we can view a smoothed version of the mesh as shown here. Notice that the minimum slip surface found in this simulation seeks out the blue or lower cohesion or weaker regions. This is using a non-circular search with a very powerful optimization technique available in slide 2 called surface altering, which we will study more in lecture 3. Now let's switch to the mesh view and turn on the slices. To calculate factor of safety here, the bottom of each slice samples the cell that it lands in. But you don't need to worry about having to use too many slices to sample your field. The bottom of each slice actually subsamples the field at 10 increments, so that if a slice falls into 2 cells, it obtains a weighted average of those cells. So because of this subsampling, 50 slices is sufficient when running spatial in slide 2. Okay, so now we have our fields and a factor of safety for each field. The next step is calculating probability of failure the same way we've done before. PF is the number of simulations with a factor of safety less than 1 divided by the total number of simulations. And this whole process of generating our random fields, finding the factor of safety of each field using limit equilibrium methods, and then calculating probability of failure is known as the random limit equilibrium method, or RLEM. And now I'll pass it on to Sina, who will show some spatial examples in slide 2.
Hello everyone, my name is Sina Javankhoshdel, and I'm going to start with a few examples in slide 2. Let's look at the first example here. In this example, we are going to show how we can model spatial variability in slide 2. This is a simple cohesive slope. The reason that we started with a simple example is the fact that there are a lot of studies in literature that use simple slopes to investigate the influence of spatial variability on probability of failure. To compare with those studies, we started with a simple example. Now let's look at the example in the slide. Here is our model. Let's look at the master scenario first. If we go to project setting statistics, you can see that the probabilistic analysis is active, but there is no spatial variability in this example. And if we go to material statistics, you can see one parameter for the soil 1 material is defined as a log normal distribution with a mean value of 45 kPa. To carry out the spatial variability analysis, I'm going to create a new model and I'm going to rename it to spatial variability. If save this model and then we go to project settings, statistics, now we can turn on the spatial variability analysis. We have two other options here. One is covariance functions that we have Markovian here. We have other covariance functions as well, but we recommend you to use the default covariance function, which is a Markovian covariance function. And the results of other covariance functions are going to be very close to this default covariance function. The other option is automatically calculate mesh size. There is an algorithm in slide 2 2018 that calculates mesh size for the user based on the geometry and spatial correlation length. If we click OK here and we go to material statistics again, we can see we have a new option here, which is a spatially variable material. We enable this option and you can see we have one more parameter or two more parameters in which are correlation length in the horizontal direction and correlation length in vertical direction. The default value is 5 meter. As Brigid said, we have a table here for the recommended values for horizontal and vertical spatial correlation lengths, that when you don't know the value of the correlation length, you can choose your number from here. And this is very easy to set up the spatial variability analysis, and you can hit the compute and look at the results at the end of the simulations. But we have a new option in a slide, which is Open Property Viewer, that we recommend you to use it before any probabilistic analysis using spatial variability. If we hit this button, you can see that you can look at the spatial field before the calculation. So if you don't like this field, or you feel that this field is not the correct field for your problem, you can play with the values here that I'm going to explain to you and change your field. Now let's look at the options that we have here. The first option is property option. We only had cohesion as a random variable, as you saw before. If we have other spatial parameters, we can choose from this option. We have filters that I'm gonna show you in the next example. The most important part of property viewer options is here. We define 2000 simulations. So for each simulation, we have a spatial field. As you can see here, we can change the number and look at the field. We can go to field 1000 or 2000. But we can't go up, so we have 2000 fields. Let's go back to the first field. The other option that we have here is to turn the spatial grid on. As you can see here, we have grids. Depends on what you like. You can choose either between the contour option or grid option. Contour option shows a smoother field, but it really doesn't matter which option you choose. The other thing that we have here is you can change the spatial correlation length and look at your field again. For example, I'm going to change it to 1 meter, and you can see how the field changes. It becomes more fluctuated. And if I change it to 100, it's going to be smoother. You can see the regions of the weak and strong material. There is an option here which is active now, apply grid changes to model. So whatever I change here, it's going to overwrite the value that was previously in material statistic dialog. Let's go back, go to material statistics, and you can see that it became 100. So I'm going to change it to 5 again and hit OK. So let's look at the results for this example. As I showed, we had 2 different models. The first one was the purely probabilistic analysis, and you can see that factor of safety is about 1.5 and probability of failure is 29.2. Right at this point, you can see that for the factor of safety of 1.5, which people use for design purposes, the probability of failure is 29%, which is very high for this factor of safety. And it shows that we need some other additional analysis, like a spatial variability analysis, to reduce this probability of failure. Now let's look at the second example. You can see that the deterministic factor of safety is about 1.5 again. Now the probability of failure is 10.1%, which is 3 times smaller than the case that had no spatial variability. And this example shows how probability of failure goes down when we have a spatial variability. We have a property viewer option for the interpreter as well, and you can look at the models after the computation as well. The field is exactly the same field that you saw before the computation. We have additional parameters for this field. One is the slip surface, the type of the slip surface, and the other one is the factor of safety corresponding to that field. This is field 1, factor of safety is 1.196. For field 2, factor of safety is 1.1, and so on. The other interesting thing that you can look here is that this critical slip surface goes through the blue region. And as you can look at the legend here, the blue region is for the weak region in the field. It means that the critical slip surface seeks out the weakest path for each simulation. And we can look at other simulations as well. Here again, you can see the critical slip surface goes through the blue region. And the most important thing here, this is limit equilibrium, but it is not a circular limit equilibrium method. It is a non-circular limit equilibrium method with optimization, and it can find any type of failure surface. It is not restricted to the circular slip surfaces anymore. For the interpreter, we have other property viewer options. One that is different from the modeler is the analysis method that you can see we use GLE or Morgenstern price. If we use other methods, we could change here. We have other filters. As you can see, we can filter the samples based on the range of the factor of safety. Now, the option is every available sample, so we can look at all the available samples. But we can look at the samples with the factors of safety of less than 1. If we hit apply, we can see that the first sample with the factor of safety of less than 1 is sample number 6 with factor of safety of 0.96. The next one is sample 15 with a factor of 0.96 again, and so on. There are other filters. My favorite is the last one, which gives you the samples closest to the mean factor of safety. Our mean factor of safety in this example was 1.16. Now, let's see what happens here. The first sample is sample 283, and you can see factor of safety is 1.16. And again, 1.16. So it gives you the samples that they are closer to the mean factor of safety. There is another filter here that it gives you the sample with the lowest factor of safety among all the simulations. If we click on that button, you can see that the factor of safety is 0.715, which is the lowest factor of safety that we had in this example, and it goes again through the blue region. Now, let's compare the results of the simple probabilistic analysis and the analysis with the spatial variability for this example. As I said, probability of failure went down from 29% to 10%, considering a spatial variability. There is something else that you can see on the left side of these figures. The critical slip surface for the case with no spatial variability is like a band. It is not spread out as the case with a spatial variability. The reason for that is, in the probabilistic analysis using a spatial variability, in each simulation we have a spatial field, we have a real field that this limit equilibrium seeks out the weakest path. So for each simulation we have a totally different failure surface. But when we do a probabilistic analysis without a spatial variability, we only have one value for the entire slope. So the critical slip surface for each simulation is similar to the other simulations. That's the first difference. The other part is, if you look at the histogram of the factor of safety, the top one is for the case that there is no spatial variability, and the bottom one is for the case that we have a spatial variability. As you can see, considering a spatial variability in our probabilistic analysis make our histogram of the factor of safety much narrower compared to the case that we don't have any spatial variability. The reason that the histogram of the factor of safety is narrower for the case with a spatial variability is that, as we said before, a spatial variability reduces the level of uncertainty in the problem. So the histogram is narrower, so we have a lower uncertainty in factor of safety, and we have a smaller probability of failure. I carried out a sensitivity analysis for this example to see what is the influence of changing the spatial correlation length. The example that we looked at was for the correlation length of 5 meters and for the case of single random variable approach. I increased the correlation length from 5 to 70 to see what happens. As you can see in the table, probability of failure goes up from 10% to 26% for the correlation length of 70 meters, and the case with no spatial variability has the probability of failure of 29%. And as you can see in this figure as well, as the spatial correlation length increases, the probability of failure also increases. The dashed line is for the case that there is no spatial variability, and you can see for smaller values of the spatial correlation length, this single random variable approach is too conservative compared to the case that we have a spatial variability. The most complex spatial variability analysis is the one that we consider both spatial variability and cross-correlation. To define cross-correlation parameter, we can use the correlation option in the material statistics dialog, and we can define the cross-correlation between input parameters here. Now let's look at the second example. This is a reinforced retaining wall example, We have two material layers, and we showed this example in our previous lecture as well, but without a spatial variability. Now let's see what happens when we consider spatial variability in this example. So the first model is the model that we investigated in the previous lecture. If we look at the project setting, we can see in the statistics section, there is no spatial variability. And if we go to material statistics, we have three materials here: the field, the blocks, and the foundation. We assume that field and foundation, they are variables, and block material is constant. For the field and foundation, as we talked about in the previous lecture, we have a correlation between input parameter. We have negative correlation between cohesion and friction angle in both materials, and a positive correlation between cohesion and unit weight and friction angle and unit weight. Okay, now we are going to create a new model with a spatial variability. Again, we go to project settings, statistics, and we turn the spatial variability on. And we go to material statistics, and for field material and foundation, we turn the spatial variability on. Again, the model is ready for computation. Let's look at the property viewer first before doing computation. Here we have, as you can see, we have two spatial material, one for field and one for foundation. And you can change the parameters from cohesion to friction angle and from friction angle to unit weight to see to look at different spatial materials. We have other filters here as well. We can show variables only, and if we go back to cohesion, you can see the blocks are constant, so we don't have any value, a spatial field for blocks here. And also you can pick materials to show. For example, we just pick field material or field and foundation. And if we change the simulation number, you can see the spatial field for each simulation. And again, you can turn the grid on or off. Let's change the spatial correlation length for each material. As we explained before, as the spatial correlation length becomes smaller, the material becomes more fluctuated. And as we increase the spatial correlation length, it becomes smoother. I'm going to show you here another feature of the property viewer. As we mentioned before, there is a negative cross correlation between cohesion and friction angle. So I'm going to show you that effect here. So if we have two spatial fields, for the second one, I'm going to change it to friction angle. And I'm gonna turn this synchronized property viewer on. When we turn this on, if we change the field, everything is gonna change for both of the examples. In this example here, if you look at the fields, for example, for the field, the top layer, you can see that the left one is for cohesion and the right one is for friction angle. The left one is mostly blue and the right one is mostly red. It shows that there is a negative correlation between friction angle and cohesion. And the same for foundation. You can see the left side of the foundation for cohesion is red and green, and the left side for the friction angle, foundation of the friction angle, is blue. So there is a negative cross correlation here as well. Now, let's look at the results. As we showed you before, the case that we have a cross correlation for the probabilistic analysis, we had factor of safety of 1.32 with the probability of failure of 6.75%. Now for the case that we have a spatial variability, you can see that the probability of failure goes down to 0.75%. So there is a huge difference between the probability of failure for the case with and without a spatial variability. The other thing here is the probability of failure that we have for the case of reinforced retaining wall with a spatial variability. As you can see here, probability of failure is 0.75%. The design value for the probability of failure of reinforced retaining walls depends on the type of failure mechanism. If the failure mechanism is external, it means that if the failure surface goes beyond the reinforced zone, the probability of failure for design is 0.01%. But if the failure mechanism is mostly internal, it has the failure surface has intersection with the reinforcement layers, the probability of failure for design can go up to 1%. And you can see in this example that considering a spatial variability reduces the probability of failure to the value that it is good for design purposes, which is very important. So far we have learned that a spatial variability analysis is important in the probabilistic analysis. Now, why there is a reluctance in using a spatial variability analysis? There are different reasons. The first reason is geotechnical engineers think that they should have too many parameters for a spatial variability analysis, while only one more parameter of a spatial correlation length is required, as you saw in these examples. The other reason is people have problem of measuring a spatial correlation length, but as we explained in this presentation, using CPD data, it is possible to measure correlation lengths, and for the cases that we have deficiency of data, we can use other approaches such as Bayesian approach to measure the spatial correlation length. The other problem was that the tools for complex geometries were not available for geotechnical engineers. But after introducing slide 2018, there is no problem of modeling slopes with complex geometries considering the spatial variability. Even though some of the tools could model the complex geometries, the speed was a problem. But again, in slide 2018, using surface altering optimization technique and using parallel processing, we don't have any speed problem. We can have any type of geometry, any mesh size, any correlation length, and carry out probabilistic analysis very quickly. In this presentation, we talked about simple cases and a reinforced two-layer retaining wall. In the next presentation, we are going to talk about real case studies, real examples that people did probabilistic analysis with or without a spatial variability. For example, this is Sugar Creek embankment that we are going to show you the probabilistic analysis using a spatial variability. If you have any question about this lecture, please email us at statistics@rocscience.com. And our next lecture is going to be about a spatial analysis in slide 2018.